All right. Hello, everyone. Welcome back to Operating Systems. Welcome back to Comp 3430. Today, we are going to keep talking about RAID. I want to talk about RAID. I want to talk a little bit about file system inconsistencies. And then what I'd like to do is take the time to go through an example with exFAT and a small code fragment to try and make decisions about what data structures are read, used, and modified as different lines of code are executing in a program. So what I want you to be able to do by the end of today's lecture is show how common file operations are performed in terms of manipulating a file system's data structures. We're looking at this in two ways. We're going to be looking at this from the perspective of inconsistent file systems with VSFS. So what modifications need to happen to the data structures in a file system that lead to inconsistent file systems? And here's some code. What happens with the data structures in exFAT if we were to run that code through a hypothetical exFAT driver? Given some requirements, choose a RAID level. I've handed out, these are up on the course webpage. We'll go through these. There are some descriptions of a person or a workload, and we're going to have to decide by comparing different RAID levels which workload is the most, or which RAID level is the most suitable for the workload that we're given. And then in terms of inconsistent file systems, I want us to be able to describe or select what a human operator might see in files and their file explorer when a file system is in an inconsistent state. So our first learning outcome here is very much about the data structures in the file system. What changes do we have to make? What changes do we make that can put a file system into an inconsistent state? And then what we're looking at here is if my parents open up Windows Explorer, what do they see? So what do they actually see if we've got a file system that's in an inconsistent state? Looking at various kinds of inconsistencies. So different parts of the file system's data structures are updated. What would they see in their file browser? All right, so want to quickly summarize RAID again. I didn't bring my controller back. Those hard drives are heavy. You don't want to carry them around, and they got enough being chucked on the floor last class. Quick summary of RAID. There's a variety of different levels, but the ones we're interested in right now and the ones that I'm looking for you to answer here are RAID 0, which is striping. We've got a bunch of disks. Just stitch them all together and get one big disk on the other side. So attach 3 4 terabyte disks to my RAID controller, and my operating system sees one big 12 terabyte disk. This is great because I get lots of space. It's great because it's fast. We can get big reads spread across all of these different drives. This is really bad because if I lose a single disk, I lose everything. I can't recover the data that's on this system. We could spend lots of time talking about, well, maybe you could actually recover data from this system, but we're just going to say, no, you cannot recover data from this system. RAID 1, mirroring, is instead of taking these 3 disks and stitching them together and get one big disk, mirroring is duplicate your data across many disks. So mirroring here is if we've got 3 4 terabyte disks and there's a write request, send the identical write request to all 3 of those drives. You have 4 terabytes of usable space, but you have 3 copies of the data. If you lose one of those drives, no problem. You just have other copies of the data on those drives that you can start working with. It's not a big deal. But you're also wasting 8 terabytes of space. You are losing 8 terabytes of space. It's fast, it's fast-ish, It's not as fast as RAID 0. There are some workloads that will cause this to be in kind of a slower state than what RAID 0 has. So things like sequential reads across a disk can cause this. Sequential reads for big files can cause RAID 1 to be slower because it has to do reads across many different tracks and sectors on the hard drives. And the other one is RAID 4 and 5, which is parity. And the goal here is to try and balance these two things. Striping gives us the most space, but we lose any kind of redundancy here. RAID 1 mirroring gives us the least amount of space, but we have the ultimate, like, greatest possible ability to recover files when a disk goes bad. Parity, RAID 4 and 5 is we've got 3 disks, just sacrifice one of those disks as the parity bit, and that will let us decide if there's an inconsistent write between across the drives, and then we can try and recover data from it that way. But instead of giving up 2 drives or all the drives, we just give up one of those drives for integrity. In terms of write performance, this is one of the slowest ones because we have to calculate checksums. We have to do the writes that way. In terms of read performance, it's approximately the same as what RAID 1 is. It's approximately the same as what RAID 0 is. It's kind of in the middle of the two things. We're going to be looking at some scenarios. I want us to take the time to look at these scenarios. We're going to step through these scenarios one at a time. Of course, they're all printed on one page. You can just read ahead if you want, but we're going to step through them together. I'm going to stage this to go through each one of them. The question that I'm going to ask you is which RAID level is the most appropriate for this situation? The options that I'm going to give you are RAID 1, RAID 0, RAID 4/5. So I'm not really separating 4 and 5, but just treating them as the same thing here, or something else. Something else could be some combination of approaches. Maybe I want to talk about using RAID 1.0 or RAID 0.1, or maybe I want to use separate RAID arrays, so have different sets of disks for different parts of the workload that we've been given. Let's start with the first scenario. I'm going to read this aloud to you. Story time with Franklin. I'm going to read this aloud to you. I'm going to pop it up the screen. I'll read it aloud to you. And then I'll give you some time to, if you're sitting next to somebody, to talk to them about it, or just think about it if you just want to think about it. Scenario 1 is the data hoarder. I feel like I have some responsibility to provide a backup service for the whole world, at least the English-speaking world that likes to watch TV shows. I feel like I have some responsibility to do this. I like to back up things like The Expanse, although The Expanse is getting kind of old now. Let's say I like to back up, I don't know, I'm watching Silo right now. Are you watching Silo? No? Yeah. I want to start watching Mrs. Davis. I haven't started watching that. I'm watching Clone High, which is like a real throwback to my high school days. Doesn't matter. I'm backing up some kind of TV shows. Okay, I'm backing up TV shows, but I only back up the highest quality TV shows. This is important data to me, but it takes up a ton of space. And I can afford lots of little disks. I can buy a bunch of these 4 terabyte disks, but I cannot afford to buy a 20 terabyte disk. I'm also aware, despite how important this is to me, that there are lots of other people backing up this data on their own local systems. So I'm not really too concerned if I lose the data because I can always get that back up from somebody else later. I'm going to give you 3 minutes. Just talk about this. Think about it for now. What's the most appropriate RAID level for this workload? I'm going to give you 2 minutes to talk about this. Give you 2 minutes, and then I'm going to pop up a Mentimeter, and we're going to get a poll. Just take a survey of what we've got going on. Please go ahead. Take 2 minutes. All right, feel free to pop something up here if you're thinking about it. I'm gonna hold for like 20 seconds to give you some time to connect and answer. All right, this is a little bit more evenly split than I expected. It's a little bit more evenly split than I expected. So in this situation, the person is a little bit, the hypothetical person is a little bit concerned about the data that they've got. They are a little bit concerned about it, but they're not too concerned about it because they can get it back somewhere else. They're most concerned about disk space. They're most concerned about maximizing disk space. In this case, I think that RAID 4 or 5 is a reasonable answer. It does increase the amount of disk space that you overall have. And we can make this argument that this person says they're a little bit concerned about this data. And so we would want to have some kind of resiliency on it. We want to make sure that there's some way to get data back if one of the disks does die. It takes time to download those files that you're backing up. So maybe you don't want to waste that time again. I think the best answer here, and I'm going to ask whoever wrote something else if they'll self-identify, but I think the best answer here is RAID 0. I think the best answer here for this situation is RAID 0 because we're trying to maximize space. I can buy lots of little drives, I can stitch them all together, and I can get the most amount of space from this. And I don't really care that much about speed. Speed is good with RAID 0, but I don't really care that much about it. I really just want to maximize space. So something else. If you are comfortable, is that you? Did you say something else? Or do you have a question? Okay, so ask your question or tell us about what your something else is, or both. Yes. So the question is, if you have RAID 0 and you lose one disk, then all of the data is gone. Yes, 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 yes.
But you don't know what you lost. Yeah, like somebody else has that data, but you don't know what you lost.
Okay. So that's a fair point. The point that's being made is we've got this giant array of disks. We lose one of them. We also lose meta information, which is we don't even necessarily know what was on that drive in the first place. Is that kind of what you're saying? Yeah. So we don't necessarily even know what files were there in the first place because we're just backing stuff up. We're backing up lots of stuff indiscriminately. We don't really care much about quality of show or whatever. We're just getting whatever we want, and we don't know what was there. Okay, that's a fair point. So what's your something else? What's your alternative here? Okay. Yeah.
I know it wasn't in the scope of the actual RAID 5.0.
RAID 5.0, okay.
So you need 6 disks for it.
Okay, so RAID 5.0 is not described in the textbook, I don't believe. Can you tell us what that is?
It's basically the 5.0 superconducting
Okay, okay.
last
Yeah,
but it basically it's told us the parity of checking features of grade zero just having
okay.
um,
So it does some striping plus parity. Okay. Okay, that's fair. I think that's a good, thank you for that. That's a good alternative. I'm gonna go back to your situation here, and one suggestion I might make for that specific thing, I don't even know what's on these drives, is to have two separate disks. One is for the actual data, and one of them is for the metadata. So like an actual, I don't know, make up like a plain text file or a directory that's full of files that are filled with connection information about how to get those files back. Some other meta information about what the files are on a separate location. Maybe that's RAID 1 or maybe that's RAID 4, but you could have two arrays. The primary array being RAID 0 for all of the data that you're storing, and the other one is going to be for the metadata, so data about the data that you've got. Yeah, that might help with that problem, but that was a good point. Thank you. Any other questions about scenario one? Are we okay? Yeah.
This one use the RID 0 because RID 4 and 5 have parity, right?
Yeah. So
You
we're
need the normal space.
we're giving up some of the space that we could otherwise use to put data on for that parity bit. With RAID 0, we're not giving up any space at all. Yeah. Okay. All right. Let's take a look at the next scenario here. This is the gamer. To be clear, this is definitely not me. You know, the newest game that I play is like Stardew Valley, which is not a game like this. The next newest game, the game that I started playing was Super Mario RPG, which is definitely not this kind of gaming situation. But I'm going to read this anyway. This describes somebody. This one says, speed is of utmost importance to me. I've got the fastest disks that money can buy. So think about this as like NVMe drives or something. We've got super fast NVMe, PCI Express 4. I don't know what other kinds of things we talk about when we're getting drives like this. But they're just not fast enough. If anybody saw that I was ever running at less than some absurd frames per second, I would be exiled and embarrassed. I know that lots of space is really good, but I don't need a lot of space since I only play one game at a time and I can always just reinstall it from Steam. What RAID level would be the most appropriate for my workload? So I'll give you a little bit of guidance here. Start to try to think about what things we're measuring about RAID levels. Speed, reliability, space. What is this person looking for? Take 2 minutes. I'll pop up Mentimeter again. We'll do the same thing. Please go ahead. You think that's too high? Okay. Did you get the whole setup? All right, I'm gonna hold here for 20 seconds, pop something up. I tried this time to hide them so that we're not influenced necessarily by what's showing up at the top. Just curious to see what shows up. Yeah, yeah. Speed. Is it for the write speed or the read speed? I'm gonna say that games are primarily a read operation. So like you're trying to read a lot of like textures and assets from the drive very quickly. There's not a lot of writing that happens. The writing would be mostly to like network, I think, more than anything, if you're playing a networked game. Yeah. All right, let's take a look at the results here. RAID 0 again. RAID 1 is at the bottom. RAID 4 and 5 are kind of in the middle, and something else, it looks like there's more than one person that has said something else this time. So in this situation, our gamer is trying to drive speed. That is the most important thing to this person. They don't care about space. They care about speed mostly. They don't care about space because they only play one game at a time. They don't necessarily care too much about reliability because they can just re-download that game from Steam if they need to. Reinstall Windows, download Steam, reinstall the game from Steam. They don't care that much about it. In this case, we might think it would be really reasonable to say RAID 1, mirroring. It would be reasonable to say that. I don't know if that was just a funny coincidence or if that happened. It would be reasonable to say that, but, okay, but, that's the other half of my sentence, but it would be reasonable to say that. It would be reasonable to say that because we can start to think about things like, well, if I'm mirroring across many disks, then I can issue parallel read requests. And it doesn't matter how slow one of those drives is because in theory, I should be able to pull from all the drives as fast as possible. That might be possible. In terms of what we've got in our book, in terms of what the measurements that they're making, and kind of in terms of practice, RAID 0 is the best answer here. This is still the fastest way to get data off of disks. It's still the fastest way to get data off of disks that are sequentially read. So when we're reading big chunks, I'm going to come to you in a second, Aiden. When we're reading really big chunks, we've got this stripe that goes across these drives. The requests that we're going to make are going to be like for block 1, block 2, block 3, block 4. I've got a 5 GB texture file that I need to read. I'm just going to sequentially read that whole thing. In a stripe, my blocks are spread across the disk sequentially, so I'm going to get parallel-like performance from that request with RAID 0 because I can read block 0, block 1, block 2, block 3 across 4 disks and get those all back kind of at the same time. Eden, yeah. Okay. Is that your something else here? Just don't use RAID at all? So, you are right. I'm going to say you're right. And I gave that, I'm going to say that you're right because of what I said in the example. I didn't write it in here, and I just kind of said it in the moment. Your PCIe 4 or NVMe or whatever are going to be able to saturate the PCIe bus. They're going to be able to send data back as fast as possible. The context of RAID here is a lot more about spinning disks. So you are right. I'm going to say you were right. In terms of spinning disks, RAID 0 is the best answer here. Yes, you are totally right. Thank you for bringing that up. The best answer for disks that are spinning that are not SSDs is RAID 0. Yeah. Okay. Were there any other something else's? Yeah. No. That is a totally fair point. Start to upgrade other parts of the system. I'm going to say two things. One is if I'm asking you a question about that has learning outcomes stated as pick RAID levels, pick a RAID level, pick a RAID level. Yeah, okay, good. The other thing that I could say to this is like maybe this person has already done that and they're just trying to eke out the very last bit of performance that they can get out of their system. So they already have a, I don't know, a Threadripper and a, I don't know what the top GPUs are right now, GTX 4010? 4090? Okay, GTX 4090, they got the top level everything, except they're running on a hard drives for some reason. I don't know. Because they can't afford to buy an SSD. I don't know. See, that's fair. That's totally fair. You're going to get better results by upgrading other parts of your system. That's a totally fair answer. But again, if I'm asking you about RAID levels, pick a RAID level. Yeah. Okay. Any other questions about this one? Any other something else? Okay, so we're optimizing for speed for this person. We've got those 3 measurements. Let's take a look at the last one. This scenario, also labeled as scenario 2. This is scenario 3. This is the scientist. This kind of actually describes me in a sort of past life. I'm a person that has several different needs. I have a large compute cluster, and I need to be able to calculate results very fast. I need to be able to take very, very large files, and I need to be able to calculate the results from those very, very large files very, very fast. Once I do a calculation, I need to be confident that what I write to disks are accurate, both in terms of long-term storage and what I'm writing right now. I need to make sure that once I've done this calculation, it is there so that I can reliably show it to someone who is questioning the results that I've got in my paper. I also need to be able to have access to lots of temporary space while these calculations are running. So I need to have fast calculations, and I need to be able to have fast read and write access while these jobs are running. I want to be able to store this in the long term to make sure that my results are accurate in case somebody questions my results in my paper. Which RAID levels might be appropriate for my workload? Take 2 minutes, pop up Mentimeter again. Okay, I got 20 seconds left on my timer. All right, let's take a look. Okay, so our top answer here is RAID 4 and 5. The middle second answer is RAID 1. The third answer, something else, what? And then the fourth answer is RAID 0. I'm gonna say that, yeah, RAID 4 and 5 is a reasonable choice to make. This person is trying to do their best to balance the needs of both what RAID 1 are and what RAID 0 are. I want some reliability and I want to maximize disk space. I need lots of disk space. Choosing RAID 4 and 5 for this is a reasonable choice to make. I'm going to straight up say that RAID 1 is a bad choice in this situation, unless it's part of something else. RAID 1 all by itself kind of means that we've got all of that wasted space just to duplicate things. And that does kind of lead to this. I need to be confident that the results on disk are accurate, and I need to have long-term data storage. That does lead to that. But the other half of this is I need lots of disk space, and I need it to be fast. RAID 1 to me is probably not the right choice there. Something else, I'm going to let somebody else tell me what something else is. RAID 0 may be a good choice, but for the same reasons that RAID 1 is bad, I'm going to say that RAID 0 is bad. This doesn't really satisfy all of the needs that this person wants. RAID 0 could be part of something else, but not necessarily all by itself. We shouldn't put everything on RAID 0 for this person. So, something else. If you feel comfortable telling me, what do you think?
One that's completely duplicated or 5, and then do like or on RAID 0.
Yeah, so that's a fair option. Take one big array that's RAID 0 for your calculations, your temporary storage, and then put your long-term results on RAID 4, 5. That is a totally reasonable option to me, yes. Yeah. That's the best option. That's the best option. Yeah, I think that's the best option. Are there other things that we didn't think of, that I didn't think of, that would be a good solution for this person's use case? Yeah.
The other thing most of the calculations would be done with the RAM, not drive.
So that's a fair question. Wouldn't the results be in the RAM? Would the temporary calculations be in RAM? Yeah, that's a fair question. And my answer to that is it kind of depends on what kind of scientist you are. A physicist is mostly going to be in memory. Mathematician will mostly be in memory. Not all physicists are purely in memory. So thinking about something like the LHC, Large Hadron Collider, they are just like dumping data constantly. It's way too big to fit in memory. It's got to go on disk. The kinds of stuff that I was doing before coming here, life sciences stuff, sequencing data, biological sequencing data, that is too big for memory. It has to go on disk. I can load stuff into memory, do stuff with it, but then I have to write it out again because it's too big for memory. I can't keep everything in memory. That's a fair point. Why not just have 500 gigabytes of memory? You laugh a little bit, but that's actually reasonable to have in a single server. That is totally reasonable. Terabytes of memory on a single server is reasonable. It's very expensive, but it's reasonable. The better answer, the bigger answer here is it depends. It really depends on what kind of stuff you're doing. I'm going to say this person just needs so much space that they can't fit it into main memory. We okay with that? Good. Okay. So when we're doing this, when we're trying to figure out what kind of RAID scenario, what kind of RAID level to choose for these different situations, the questions that I'm really asking you to accomplish are to try and identify what the needs are for this workload in terms of those 3 metrics that we're using for measuring performance of RAID levels. So capacity, speed, and reliability, and then use those to inform the decision that you'd make for whatever this person or this workload happens to be in terms of what they want to accomplish. That's really what we're trying to do here. Compare the different RAID levels on those 3 properties and then make a decision about what is the best one for the workload that we've got. All right. So RAID does not know anything about file systems. RAID doesn't know anything about file systems. RAID is stupid. RAID is dumb. it accepts write requests and it responds to read requests. It doesn't know anything about data structures. It doesn't know anything about file systems. It does not know or care about your data. File systems at a higher level of abstraction and our operating system, they know about data structures. They know a little bit about your data. And when we're writing file systems, when we're writing data out in file systems, unfortunately, even though we've got an atomic operation in the form of I can write a sector out, making changes to data structures in file systems is not an atomic operation. It can't be an atomic operation just due to the nature of what our disks look like. They're kind of spread across different tracks and sectors across a drive. File systems can become inconsistent. So an inconsistent file system has nothing to do with your data. It doesn't know anything about your data. It has really zero to do about whether or not your bitmap or your video or whatever itself is a valid piece of data. It's all about the data structures in the file system itself. And it's all about whether or not those data structures agree with each other about what the state of the file system is. Data systems, file systems can become inconsistent in very creative ways. We're going to take a look at an example of extending a file. And so this is adding a new block to an existing file. And the steps that we're taking here are we are opening a file for read, we're writing to the file, and then we are closing the file. This is the file system that's the teeny tiny version of VSFS that's described in our book. And it consists of 4 different parts here. We've got the bitmaps. These are our allocation structures. The inode bitmap, we've got one little slot here for every one of the inodes in our inode table. Presence or absence or used or unused is marked with color here. So this one inode here is used. The data bitmap works approximately the same way, but it refers to the data blocks in the data region. When we make a change to a file, we have to make changes to these data structures across the different parts of the system. I've got a file, I've opened it, I've made changes to it, I'm going to write it back out. I'm going to say that the change that I'm making here causes the file as it is right now to become one inode or one block bigger, sorry. So we add another block to this file. To do that, we have to update the inode. It's got one new direct pointer. And the file size is slightly bigger. We have to update the data bitmap. We're going to use a new block for this file. We have to find an unused block, and we have to then mark that block as used when we're writing stuff out to it. And we've got to update the data region for the actual data that we've got. In this situation, adding a new block, extending an existing file, we don't need to update the inode bitmap. We're not allocating new inodes here. We're just allocating new blocks, so we don't have to update the inode bitmap. We have to update the inode itself. I'm going to go through and describe the things that can happen as a result of having inconsistent file systems, where an inconsistent file system is the result of one or more of these operations not happening while we're in the middle of updating this file. So if I update just the data bitmap and the data region, but can't update the inode, I succeed in these two, but I crash before this one happens. What does the file system look like? What does our operator see? There's 4 options. The file looks corrupted. So we get the file back, our system comes back up, we go file open and we try to view it, but there's a bunch of garbage data in our file. Another option is there's less space available on the volume. I open up my File Explorer and I look at drive C and suddenly there's one less block. Let's pretend for a second that we can see blocks on it instead of megabytes, but there's one less block than there was before. The file's size itself is slightly bigger. So the file looks bigger. When we look at the inode itself, it reports that there's more bytes in this file. And then the other option is there's no apparent difference. We can't actually see anything wrong visually if we open this up in our File Explorer. One or more of these things can happen based on the different things that can happen to our data structures, the combinations of things that can happen. I'm going to bring this up as a Kahoot. I'm going to describe to you different scenarios that can happen. And these are the 4 options that you will always have. The 4 options that I have in this Kahoot are pictures, though. I haven't written these words out, so I want to show you what the pictures look like before we get to the Kahoot so you have a sense of what they mean. And so you could try speed running, I don't know, if you're trying to be competitive. This is what you're going to see for a corrupted looking file. I've opened up this bitmap file. I've extended it by 1 block, but now when I open it up in Paint again, there's just a bunch of garbage on this side, just a bunch of extra stuff. So the data blocks for this file are being read, and this is what we're getting back out of it. This is less space available on the volume. We had 7 blocks free before. Now we've got 6 blocks free. The file size itself is bigger. So again, pretending that we're looking at this as sizes in terms of blocks, but the file size itself has changed, or there's no apparent difference. We cannot see any differences anywhere with the data that we've got. Let's do a quiz. I'm going to pop this up. We'll do classic mode. I'll give you a little bit of time to join. Pizza Pips. Hold for 10 more seconds or something. But the pin stays up at the top the whole time. Yeah, there are no loud kids. Yeah, I just noticed that too. Now that you read that, there's no loud kids next door today. That's great. Good. Digression, to complete digression. My partner is a middle school teacher, and she is on campus right now with 150 middle schoolers. But they are all over doing track meet stuff on the other side of the stadium. And I'm really grateful that I don't have to go over there and quiet your kids down. Okay. So all of these questions are going to be, here is what's been written. These are the options, and I'll try to let you know if there's ones where you have to pick multiple things. Like this one, you have to pick multiple things. Okay, all right. So we've updated just the inode. That's the only thing that's been updated. I'm going to go back here. I'm going to go back up to this diagram right here. We've updated just the inode. The only thing that has changed is this. That means that we've updated the inode with a direct pointer and we've changed the size of the file, but we haven't written anything in the data region yet. Nothing is written to the data region. So whatever happened to be in block 5 here is what's going to start showing up in the file, because that's what we're pointing at with this direct pointer that we've got. The other half of this is that our file size has grown slightly because we've updated the inode. The inode is where we're keeping track of how much bytes or blocks this thing points at. In this case, this part here, the amount of free space available on our system has not changed because we didn't update the allocation structure. We didn't make changes to the data bitmap. The data bitmap is what's being used here to describe how much free space there is on the system. We didn't change that. We haven't marked that block as used, so it doesn't change the amount of free space available. We're okay with that? Good, 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 good. Okay. Pizza Pips. Okay, good, great. If all we do is the data bitmap, so I'm going to go back to my diagram here again. We only update the data bitmap. We don't update inode. We don't write the data block. The only change that we would be able to see is that there's less free space available, but no inodes point at that block that has been marked as used. Yeah. Like in practice or in this situation? In practice, it's kind of arbitrary what the ordering is that you do. In this situation, we're just saying that those other parts didn't happen at all. Yeah, yeah. So in practice, like if you look at the ext2 source code, I have no idea what order it is, but it's kind of whatever the author of ext2 decided to do. Yeah, yeah. So we haven't written any data out, so we would not see a corrupted looking file. We haven't changed the inode, so we would not see a corrupted looking file because we haven't had the inode updated to point at this extra block. And we wouldn't see the size of the file change because the inode itself hasn't been changed. Good, we're good, good, good. Oh no, Pizza Pops. One time I gave a quiz like this where it was the same options for every question, but I made the mistake of turning on the randomize option order. And people were actually getting mad, like quite upset that it was changing because they couldn't stay up at the top because they had to look at the options to decide which one to pick. I hope they weren't getting mad at me. We've updated just the data region. If we've only updated the data region, we haven't made changes to our inode, so the size of the picture doesn't change. That extended bit that we tried to create did get put into our data region, but our inode doesn't know about it. It was written, but our inode has no idea that it exists. The size of our inode doesn't change. When we open the file, we're using the inode to decide what the contents of the file are. The inode doesn't know anything about the extra block, so we just have the original contents of the file. The data bitmap wasn't changed. So we're not changing how much space there was available. We've just written to the data region without saying that that block has been used. So in this case, there aren't any observable changes. Okay with that? Good. I think most people got that, so great. Yes, please. That's a fair question. We're writing data here. So let's say that we've used up block 5. The way that we know how much free space is not by what's written here, it's by what's been marked as allocated here. Writing here does not mean that we have written here as well. So we're saying in this case that all we did was write bitmap data to block 5, but we haven't marked it as used in the data bitmap. So when we open up File Explorer and look, the drive appears to have the same amount of space. It does, because nobody knows, the inode doesn't know that that data block has been written. Nobody's pointing at it. Now here's a little aside. The last one, where we updated the data bitmap but didn't update the inode or the data region, is a space leak, because we can't use that block. It's been marked as used, and when we're looking for a block to use for an inode, we're not going to use it because it's been marked as used, even though nobody points at it. This is not a space leak. This situation here is not a space leak because we're just going to reuse it. We're just going to write over it because it hasn't been marked as used. Yeah. Okay. It's just an empty block. We don't know what's in it. We don't care. Brett. I feel like everybody should call themselves Brett next time. This is a multi-select. You must choose multiple options here. Yes, good. Good, that is excellent. We've updated the data bitmap and the inode, but we didn't write the data itself. So we've marked that a block has been used. We've updated an inode to point at that block, but we didn't write any data to that block. Whatever garbage was in that block is what we're going to see in this file. The inode has been updated with the direct pointer to point at that garbage. The inode has been updated, so the file size has increased. The data bitmap has been updated, so the file system appears to have one less block allocated, even though the data that we tried to write never actually got written. Good. This is like shifting constantly. Sorry, what's that? This one is just pick one. Good, good, good. If we update just the data bitmap and the data region, but we don't update the inode, so when we don't update the inode, we're not pointing at the block that we've written. We have written the block, but we're not pointing at it. The inode doesn't know that that block exists. We don't update the inode, so we don't change the file size, and we're not pointing at garbage data because as far as the inode is concerned, we still have just the original contents of the file. We are not referring to that extra stuff as another inode direct pointer. Updating the data bitmap means that we've got less free space on this volume. And in this case, we've also got that space leak situation. We've written something valid there. We can't get it back. We can't point to it. We're not pointing at it with anything. We're not going to be able to overwrite it with something else because it's been marked as used by an inode. Okay with that? Good, good. Okay. We got 2 more here. This one is just a pick one option. All right, okay. So we've updated the inode and the data region. Let's go back to our diagram here. The inode and the data region. We've updated the inode, and we've changed the size of the file. We've changed the size of the file, and we've changed the direct pointers for this inode. So we've got 2 blocks. We're pointing at 2 blocks now. We're saying the size of the file is 1 bigger. We've written to the data region with the actual data for the file. The inode points at both of the blocks that we've got. So when I bring this file up, it's going to look as though it's bigger. The size of the file has changed. That's what we expected to see, that the size of the file has changed. It's not a corrupt looking file because I wrote the block out. I added a new block to this file and I wrote the actual contents of that block out, but I didn't update the data bitmap, didn't make changes to the bitmap itself, the allocation structure. Nobody picked this. That's good. We have not made changes to the allocation structure. So the amount of disk space free has not changed. Do we see maybe a little problem with this situation here? The file has gotten bigger. The amount of free space has not changed. The amount of free space has not changed. To be clear about this, though, we're not seeing this option because we actually wrote correct data out to here. So let's say that by extending this picture, I've added Walter. I added Walter, my cat. We'd actually see Walter, my cat here. We wouldn't just see whatever garbage happened to be there before that because we succeeded in writing that data out. We okay with that? Okay. The next question is related to this one. The next question is a multi-select. You have to choose multiple things. It's the same question, but let's leave it for a while. Let's just keep running the system. Good. Okay. We've updated the inode and the data region. We updated the inode. We're updating the direct block pointer and the file size, and we've written out correct data originally. This is still true. The size of the file is bigger. But because we did not update that allocation structure, we didn't say this block is used by somebody. Our code, our file system code is going to be like, I need a free block. There's a free block. I'm going to write my essay.docx on this block that was originally my bitmap picture. And it's just going to write what appears to be a bunch of garbage there. And we're going to be in the state of this block here, the new thing that we added to this original file, will have 2 inodes pointing at it. One block should have one inode pointing at it, no more. An inode points at many blocks maybe, but one inode should only have one block pointing at it. One to many and then many to one. Yeah, yeah. Yeah. So that's a great point. If I've got my image here as this half, and then I open it, hey, somebody overwrote my file, I'm going to draw a picture of Walter again and save it. And then I open up my essay.docx. Now it's going to be like, I don't know what word is going to actually show. It'll show like wingdings or something, right? A bunch of wingdings instead of my essay. And I'm going to be like, hey, that was my essay. I'm going to rewrite it. Type, or open ChatGPT and just get it to type it for me. Save it, and then I'm going to open up my picture.bmp, and it's going to be like, hey, who overwrote Walter? Yeah, back and forth constantly. We've got two different inodes that are pointing at the same block. Our human operators might argue about it at that point. Yeah. Okay, all right. Prairie Dog. Congratulations, Prairie Dog, whoever you are. Okay, so these are the interesting ways that our file systems can become inconsistent in this type of a file system, so VSFS and EXT. We've been going through two different file systems. We've been talking about this one, and we've been talking about EXFAT. However, you should be able to make the same kind of conclusions for EXFAT based on what you're seeing here. EXFAT has an allocation structure. I did not draw this allocation structure in what I was describing originally because I was just generally describing FAT file systems. But as you're reading through the documentation, it's starting lab 3. You're starting lab 3? Yeah, yes, yeah, good. As you're starting lab 3, you're seeing that EXFAT has an allocation structure. It is a data bitmap, except it's referring to clusters in the cluster heap. We don't have inodes, but we have all these directory entries. Some of those directory entries refer to clusters. Some of those directory entries refer to how many bytes this file has in it. We don't have inodes, but we have a FAT. And we're building cluster chains. And if the cluster chains are not updated correctly, we don't have direct block pointers. We don't have direct block pointers if we don't make changes to the FAT itself. And we have a cluster heap. We have a data region. We can write to that cluster heap and data region. You should be able to draw the same kinds of conclusions about EXFAT as you are right now with VSFS based on what we've been seeing here. Okay. I'm actually going to do something now that I didn't put in the slides because I was kind of just like really hurriedly doing this before class started today. And what I want to do is build a little bit more on the show how common file operations make changes to data structures that we have. Whoa, I'm so sorry. That we have in a file system. So I've got here an example of EXFAT and a small piece of code. And I'm going to amend this small piece of code in one way. This diagram is up on the course webpage, so you can also find it there if you want to have an electronic copy instead. But I'm just going to give you all printouts because I took the time to print it. And I like to draw on printouts. And I'm projecting myself onto you. Okay, so I'm going to pop this up on the screen. Here's the diagram that you got in front of you. We've got a couple of different spots here. I have written some code. Here is some C code. I've given us a FAT that has lots of FFFFF in it. There are not very long cluster chains in this FAT. They're all mostly just one cluster. We've got some information from an MBR, from a main boot record or main boot sector. This at the bottom, this is the file system structure that we've got in this file system. And then this is our cluster heap here. I've tried to draw something that's a little bit more realistic in terms of what EXFAT actually looks like, in that I now have an actual allocation structure here. What I'd like to do is step through these lines of code and start thinking about how these lines of code are referring to and using these data structures, and which lines of code are making changes to data structures. I'm not necessarily talking about tiny attribute changes, but like major changes to the data structures that we've got here. I'm going to start, and I'm going to give you like a tiny bit of time to think about this on your own. But I'm going to start by saying that this line of code doesn't really do anything. To the file system, it allocates an array. Yeah, okay, good, good. I'm glad we're all on the same page about that one. The next line here does something interesting. This does something really interesting with data structures. I'm going to ask you to start thinking about this by yourself. Talk to your neighbor, do whatever you want. But the hint that I'm going to give you about approaching this problem is that we've got to decompose this string into parts. We have to do that. We have to decompose this string into parts. And this very first slash here at the beginning of the file name is the root directory. This is the root directory. So what I'm looking for you to do right now is two things. Build a fat chain, build a cluster chain, and start looking at which data structures are being referred to. The fat is a data structure, the cluster heap is a data structure, the MBR or sector are data structures. Take 2 minutes, and then we will step through this together. 2 minutes is, to be clear, not enough time for you to actually get through all of it, but I want to make sure that we have time to talk about it together. Okay. Okay, so I know you're kind of maybe midway through this, but I want us to have time to work through it together. We're going to start with this line open. And we're making an assumption, and this is an assumption that you can make for when you get to the assignment, that all paths are going to start at the root directory. In practice, when you open a relative path, like something that doesn't start with a slash, that kind of implies that your process has state about what the directory is that it's currently in, and it uses that as a starting point for open operations, but we're just assuming that we're starting at the root directory here. So in terms of the data structures that we're going to be using to satisfy this open call, we've got to try and find out if these files and directories actually exist. If they don't exist, we have to return like -1. This is not a file. This is not a file that we can actually use. So in this file system, we're starting with the root directory here. And the root directory, we're going to be referring to this first cluster of root directory in our main boot sector. This is just one of those properties that's been given to us. To build up the first cluster of root directory, we should immediately refer to the file allocation table, to the FAT. It's possible for us to go to the cluster heap directly. We could do that and then go back to the FAT later if we wanted to, but in my mind, it's easier to build the list first and then go do the cluster stuff second. So we build up the cluster chain here. We look at location 1. That says location 3 is the next cluster for this. Cluster 3 has the end of cluster marker, end of cluster chain marker. So the list for the root directory is going to consist of cluster 1 pointing at cluster 3, pointing at null. So far, we have built up a linked list from this file allocation table structure. We have not referred it all to our cluster heap at all yet. But now that we've got that, we've got to actually start referring to the cluster heap. We have to start referring to the directory entries that are in the cluster heap. The root directory is a directory, and so we can immediately start interpreting all of the data that's in the cluster heap, starting at cluster 1, as a directory. It's full of directory entries. When I'm going through this, I'm going to open up this cluster. I'm going to start operating on this cluster. But what I'm looking for now is a folder, a directory that has the name dir. I'm going to have to start scanning through directory entries in this cluster to find a directory and to find a directory that has the name dir. The first directory entry here is of type file, so I'm going to ignore it. This is a file. That means that I can kind of skip all of these entries until I find the next file directory entry. The next file directory entry here says that this is a directory. That's a good sign, but now I'm at the end of the cluster. We're in the middle of an entry set. We're at the end of a cluster, so I need to seek to the next cluster in the chain. So I seeked to the beginning of the cluster heap. I got to cluster 1. Now I need to seek to cluster 3. I can see that I've got the stream extension for this, and then I've got file name dir. So I've found a directory that has the name dir. I've referred to the file directory entry, and I've referred to the file name directory entry. The stream extension for this is telling me this other directory entry is saying there's 4, this is at cluster 4, starts at cluster 4, and it is 128 bytes in size. So it's going to take up one full cluster. We've got one sector per cluster. Each cluster, each sector is 128 bytes. With that, I want to continue because I know that this is not the last thing that I've got in this path. The next thing that I'm going to be looking for is a file that's called hi.txt. I'm going to start at cluster 4 because I want to look in this directory to see if there is a file with that name. If I go to cluster 4 here, it immediately has the end of chain marker. So there's only one node in this cluster chain, and that is cluster 4. There's only one entry set in here, so I can look at this file and say it's a file. Great. I'm going to look for the file name. It is hi.txt. That is great. That is perfect. That's exactly what I'm looking for. If I went through this directory and I went through all the directory entries and I could not find hi.txt, or if I can't find any part of the path before it, I would immediately return -1. There is no file that has this name in this directory, or there's nothing that has this name itself. Once I open that, then internally, we're going to modify our open file table. We're going to say it points at this inode, it points at this directory, it points at this cluster, it points at this entry set in my set of entries for the directory entry for this. So I'm going to open up this file. This is my file here. These are the directory entries for that. And at that point, for the open system call, we're kind of done. We don't have to do anything else. We haven't read anything yet. We don't refer to any more directory entries. We don't do anything else with the cluster heap. All we've done is find the file that we were looking for. With the read system call here, this is our next line. Now we're taking that file descriptor that we got back, and we're starting to actually read the contents of the file system. We're reading 128 bytes of data from our file system into this buffer. In terms of the data structures that our file system is using, we're going to be making reference to the entry set for the file that we've got here. We're looking for this file. It starts at cluster 5, and it is 128 bytes in size. So the read operation is going to take everything that's in that cluster here, this whole thing, and it's going to just jam it into this buffer. It's going to read everything into the buffer. We're not changing any data structures because we're just reading from the file system right now. The write operation is going to make changes to our file system. We've opened this file. We're going to say that we've opened it for read, write, and append, so we can add stuff to the end of it. Now we're kind of taking that whole block that we read into our array, and we're going to try to write it back out again. Stuff's got to change here. Stuff has to change here. The first thing that we need to do is find an open block, an unused block. The way that we're going to find an unused block is by finding our allocation structure. To find our allocation structure, we have to open the root directory again. The root directory, the entry set for the root directory, has an entry for the allocation bitmap. So there's one entry for that, and the allocation bitmap directory entry tells us which cluster the directory, which cluster the bitmap is in. So we've got to open that up. We scan through all of them again in the same way that we did looking for the name of the file, but this time we're looking for the allocation bitmap itself. It tells us that it starts at cluster 6, so we can go to cluster 6, and then at this point we can find an entry in this that is not used. So we'll look through our bitmap here, and we're going to try to find out which one of these is not used. 0 is technically not used, but I'm just going to say we're not going to use 0. We'll find the next one after that's free. The next one after that's free is block cluster 7. So with my write operation, I'm going to update this allocation structure. I'm going to reserve this block for my use. I also want to actually write that data out. I want to say I'm going to write it into block 7. So I'm going to take the data that I've got in my file system here. I'm going to copy it, and I'm going to paste it right over here. So my write operation has now modified the allocation structure. It's modified my cluster heap because I've added this new set of data. We also now have to modify the stream extension for this file. It's now 256 bytes long. We don't need to change the first cluster, though. The first cluster is still the first cluster. That part hasn't changed. We do, however, have to modify the file allocation table. We've now said that this file consists of 2 clusters, where before it consisted of only 1. The cluster chain for this file, I'm going to build this up outside. It started at 5 before, and before it went to null, it was a linked list of size 1. But now I've actually inserted a node into this linked list, and now it should point at 7, and then it should point at null. I've added an extra cluster to this thing. For this, I need to make changes to my FAT, and the changes to my FAT are that I've got to replace this entry in the FAT. The entry at 5 is now 7, and the entry at 7 is now the end of cluster chain. It might have been that before, but I'm also just going to update it to make sure that it actually does say that. So that's the whole write operation. We're going to go through our allocation bitmap and update that. We're going to update the data in the cluster heap itself. We're going to change the file size. This is kind of like our inode in exFAT. We're going to change the file size in this stream extension directory entry. We're going to change the FAT so that we have the actual data that we've got for this extra thing added to it. The close system call doesn't do anything to our data structures. It's removing that entry from our open file table, and we're not making any changes to the file system after that. Okay, thank you for giving me some extra time. I appreciate that. Thank you. Quick summary, there's different RAID levels. They serve different needs. Different inconsistencies in file systems have different external appearances. I fixed that one so that it actually makes sense now. And it's different for each kind of failure scenario. Thank you all. I will see you tomorrow. Have a great night. Bye, everyone.